Let us look at the first example, which covers the different topics we have discussed in the previous videos. So the 300 kilogram block A is released from rest. If the masses of the pulleys and the cord are neglected, determine the velocity of the 20 kilogram block B in 2 seconds. And we have a nice schematic of the cord and pulley setup on the right. So I'll give you a couple of minutes to try to solve the problem. Remember, we're dealing with kinetics, so you can make use of the kinetics equations now, as well as the kinematic equations if needed. You can follow the steps we have discussed in the previous videos and try to solve the problem on your own. Whenever you're ready to check out the solution, simply continue the video. So step 1, as usual, is to write down what we know. We are given the initial velocity of block A, so VA0 is equal to 0. We know the mass of A, which is 100, and the mass of B, which is 20. We also know that we're actually dealing with a rope and pulley setup, so we will eventually face the dependent motion analysis. So a couple of comments about the problem, sort of conclusions one can make by reading the problem statement. First, we're dealing with the dependent motion analysis, so we need to make use of the equations and the method we've seen in the dependent motion analysis video. We know that we're dealing with two bodies, and we're asked to find the velocity of the block B in 2 seconds. So it is also nice to draw a sort of schematic which represents the different steps one needs to follow. So if you look at the given, we know that we have the mass, which means that we know the weight exerted by that mass. This means that we have information about the forces, and we know that we're looking for the velocity, so one needs to make a link between acceleration and velocity. And so if we want to nicely split up the solution of this problem, first we'll work out the kinetics and sort of link the forces to the acceleration, and then the next step, in order to get the velocity, it is a must to make use of the kinematics equations, and so we'll find a link between acceleration and velocity and then solve the problem. So this is the methodology we'll adopt. The different steps that you will see now are exactly the same steps you've seen in the videos. And so what I like to do is just to have a systematic way of solving problem, so you can follow exactly the same steps, whatever the problem is, and get the final answer. So step 2, as you might know, is to draw the free body diagram of the different bodies. Here we're dealing with two bodies, body A and body B, so we need to draw the free body diagram of both. So let us start with the free body diagram of A. We can nicely draw a box and then mark the different forces. Obviously, block A is subjected to weight since it has a mass, so we can write down MAG, and we know that it's attached with a rope, and so there's definitely a tension exerted by this rope onto the block, so we mark that with T2. Now, one thing to note when dealing with rope and pulley systems, in kinetics particularly, is to draw the free body diagram of any pulley that actually includes 2 or more different ropes. So if you look at the figure on the right, you'll notice that the pulley that's attached to block A actually interacts with 2 different ropes. The first one, which is marked here in yellow, is directly linked to block A, while the second one, which runs all along the setup and is drawn in green, actually drives block B. So it is always a good practice to draw a free body diagram of that pulley. So let's do that. So we know that from the bottom, we have the tension due to the yellow cord. And remember, again, another remark about cords is that the tension inside the cord is the same along the whole path. So if you take a cord and cut it at any position, the tension inside would exactly be the same. What's also important to note is that whenever you're dealing with a single rope and you cut it in half, as we're doing here by splitting the pulley setup and the block A, the tension that's exerted from one side is equal and opposite in direction to the tension from the other side. So we can write down here that the tension T2 exerted on the pulley is downwards, while the tension T2 exerted on block A is upward. Similarly, since we have a tension downward T2, we also have tension due to the other cord, which is highlighted in green. And again, since the cord is in contact with the pulley in two different sides, we have two different tensions acting on the pulley. And the tensions are also identical since it's exactly the same rope. So we can mark T1, T1 on the upper side. So one can conclude from the free body diagram of the pulley that T2 is equal to 2T1. And so we can replace the value of T2 in block A with 2T1. Now it's time to draw the free body diagram of block B. Similarly, we have the weight of block B, so MBG. And we also have the tension that's exerted by the rope. Again, looking at the figure on the right, you'll notice that it's the green rope that's actually in contact with block B. And remember, we have labeled the tension of the green rope by T1. So eventually the tension exerted by the rope on B is T1 as well. The next step is to draw the kinematic diagrams of A and B. Since we do not have any idea about the direction of the two blocks, one can assume both of them to be downwards, since we have selected a reference to be positive downwards. Remember, whenever you do not know the direction of the A vector or the MA vector, always assume it to take the positive direction. And if you end up with a negative value for A, it means that the vector needs to be reverted. Now that we have drawn the two diagrams, the free body diagram and the kinetic diagram, we can move forward and write down the equations of motion for A and B. Noting that the motion of block A and block B is along a straight line, we're dealing with a rectilinear motion problem, and so our problem is in 1D space. So we only have a single equation of motion per body. So doing that for A, sigma F is equal to ma, and by summing the forces, again taking the sign convention we have adopted from the beginning of the problem, positive downward, we have mg minus 2t1 is equal to ma aa. Similarly, doing that for block B, sigma F is equal to mb ab, and one can write that mbg minus t1 is equal to mb ab. So those are the two equations of motion. Remember, in the plan we have set up in step 1, we know that we need to find the acceleration in order to find the velocity. So let us look now at the two equations and look at the number of unknowns we have. So from the first equation, T1 is a known and AA is a known. Regarding equation 2, we have AB, which is a known, and T1, which is already an unknown. So in total, we are dealing with three different unknowns, T1, AA, and AB. Now, unfortunately, the equations of motions only give us two equations since we're dealing with a 1D problem. So we need to add an additional equation in order to solve the problem and move on and then calculate the velocity. So how do we get this additional equation? Remember from the notes of the previous videos, we know that additional equations can be found by using the kinematic equations. We know that we're dealing with a dependable motion analysis problem, so we can make use of the dependable motion equation. So let us do that for step 5. Let us write an equation for the rope. And to do so, if you remember from the section on dependable motion in chapter 12, there are a couple of steps we need to do before we actually write the equation. So first, we need to select the datum lines for both bodies. Remember, the datum line needs to be fixed. So in this case, I have decided to pick a datum line which is connected to the upper fixed surface. Next, we need to highlight the positive direction. Remember, the positive direction whenever dealing with dependable motion is always outwards, out of the datum line. So the positive side is downwards in this case. And then we can mark the positions A and B, so SA and SB. Now notice I have marked SA to be connected to the pulley and not to block B. And that's because we can get rid of any constant parts. So the distance between the pulley and block A is always the same. So there's no point in labeling SA to be the whole distance. So if one needs to write now the equation for the rope, we're now ready to do that. Remember, we need to sum up an equation for the rope that's actually moving. So the two ropes that are highlighted in yellow here do not move, and so we do not need to write any equation for those. The main rope that we need to write an equation for is the green one. So let us do that. We simply need to sum the different chunks of the rope in terms of the distance SA and SB. So summing up all that, we have 2SA plus SB is equal to L. And then the next step is to take the derivative. We get 2VA plus VB is equal to 0 since L is a constant and the derivative of a constant is 0. So 2VA is equal to minus VB. That's the first expression we get. Now we're actually interested in the acceleration, so we need to take a derivative again. And so we end up with 2AA is equal to minus AB. So that's great. Now we have a third equation. 3 equations with 3 unknowns. We can easily solve for AA and AB. So let us write down the equations again. We have 981 minus 2T1 is equal to 100 AA. 196 plus 2 minus T1 is equal to 20 AB. And 2AA is equal to minus AB. 3 equations with 3 unknowns. We can solve the system. I will not go over the details regarding the calculations. I assume that you are able to solve the system on your own. And so you'll end up with the 3 different variables. T1 is equal to 327 newtons. AA is equal to 3.27 meter per second square. And AB is equal to minus 6.54 meter per second square. Now what does the sign actually mean here for AA and AB? Well, we need to compare that to the sign convention we've adopted, which is positive downward. So 3.27 means that AA is 3.27 downwards. And minus 6.54 meter per second square is 6.54 meter per second square upwards. So it's very important to relate back to the sign convention that you've adopted at the very beginning of the problem. So now that we have the acceleration components, in step 7, we can use the kinematic equations to get VB. Remember, we've seen here from the equation of motion that A is a constant. And since A is a constant and we know that A is equal to dV over dt, we can simply apply the integration and get an expression for V as a function of time. So performing integral of dV is equal to integral of A dt, we get V minus V0 is equal to AT, and V is equal to AT plus V0. We've done that a couple of times now, so I will not dwell on that. Once we have an expression of V as a function of time and the acceleration, we can simply replace the different terms. Remember, we're looking at the velocity for t equals to 2 seconds. So V is equal to 6.54 times 2 plus 0 since V0 is equal to 0. And we end up with a value of 13.1 meter per second. Now notice in the expression I have replaced AB with 6.54 and not minus 6.54 because I already know the direction of A. And so V would obviously have the same direction of A. So 13.1 meter per second actually means that V is 13.1 meter per second upwards. So this is a nice problem which summarizes everything we've discussed so far. Remember, the steps we've used here are exactly the same for any other problems related to kinetics. So you start by writing down what you know from the given, then you analyze what you know from the given and come up with certain conclusions concerning the problem. Once you have these conclusions, you know how to move forward. Step 2 is to draw the free body diagram. Step 3 is to draw the kinetic diagram. Then you apply the equations of motions. You sum up the different unknowns. So you add up all the unknowns and list them. And if the number of unknowns is more than the number of equations, you need to look back at the kinematic equations to add to the problem. Making use of the kinematic equations and the kinetic equations, you should end up with an equal number of unknowns and equation. Then you solve your system and get the value you're looking for. If the value you're looking for is not acceleration but velocity, you need to do an additional step which involves only kinematics, and so you use the fundamental equations of kinematics to find V from A.